Okay, last little part with area under the curve and looking at, I suppose, a single curve is going to be to do with areas going above and below the axis. And I suppose a little part maybe that should have probably mentioned earlier, but we're mentioning it here and everyone should be following them through. So hopefully you've watched the previous ones and are into this one as well. But a little thing to talk about with area. So area as it stands, as a quantity, as its definition, is that area is positive. It's a kind of a marker or a kind of measure of space. And as such, we don't really think about areas being negative. And we'd see that obviously when we look at kind of calculations in area and volume and that sort of thing, but the same thing applies here. So area by definition is considered to be positive. Now the calculations that we're doing with integration can result in positive or negative values, and that is largely going to depend on where you're integrating. The examples and the questions that we looked at above were mostly integrating, or were all integrating above the axis, okay, as we can kind of see here. And when I'm integrating above the axis, the area or the answer to my calculation is going to be positive, and the result that I'll get will be positive. Okay, and that's if I'm above the x-axis, and as I've said here, if b is greater than a. Okay, so that maybe is one of the ways we can kind of counteract this if we so choose. But when b is greater than a and I'm above the x-axis, then the result of my calculation is going to be a positive answer. If the area or the calculation or the region that I'm looking at is below the axis, then the result that I will get from my calculation will be negative. What is important though is to note that the area will have to be positive. So we will have to take an absolute value of that or make it positive when we're looking at areas below the axis. Okay, otherwise we kind of are falling out of that definition of area kind of as it stands there. So it's just important to look at kind of, or to have that understanding and that concept that the areas above and below the axis will have different signs, or the calculations I should say, so we must adjust that then when it comes time to work out total area, or even just to work out area itself. If the question I was doing was solely one area and it was just below the axis, I would need to acknowledge that the calculation I'll do will give me a negative answer. It does not mean I'm wrong, but I must make it positive in presenting my overall solution. When I'm writing down that the area is whatever, I don't give a negative answer there, I give a positive answer. Okay, in terms of the y-axis, same idea, right is positive, left is negative. Okay, so kind of that same idea of above and below. Okay, where this becomes particularly important is when we're looking at curves that go above and below the axis. So looking at these curves here, I suppose a cubic curve is kind of a prime example here really. But if I want to find the area that's bounded just between the curve and the axes there, and I have regions above and below, I need to separate those areas, because if I don't, then the calculations are going to kind of affect each other, because I'll have part of a positive answer, part of my answer will be negative, and then that's going to kind of affect my overall calculation for area, particularly with cubics where a lot of them end up being symmetrical really with the regions that you're finding above and below the axis. So then you can nearly even end up kind of getting an answer of 0 because the regions that you're looking at have nearly are just the same, but the signs are different, so the calculations just end up nearly cancelling out altogether. So we have to be careful to just separate the two areas when we come to doing the calculation. Once you've done that, it's the same as normal, with just that acknowledgement that the region below the axis will give me a negative answer, but the area still needs to be made positive. Okay, so we look at that in an example here. Find the area enclosed between the curve f of x equals x cubed minus 2x squared minus x plus 2, the x-axis, and the lines x equals minus 1 and x equals 2. Okay, so all that really means is we are looking for the region here and here. So they're looking for the area between the curve and the axis between those two x values that I've been given, and part of that is going to be above and part of that is going to be below the axis. I already am making my kind of mark for myself that the region above the axis is going to give me a positive answer, the region below the axis is going to give me a negative answer. Okay, and we can kind of give them name. We can call this A1, we can call this A2. So we'll just remind ourselves that the total is going to be A1 plus the absolute value of A2. Okay, and that's us making that acknowledgement and reminder for ourselves that even though the answer to A2 is negative, is going to give me a negative result, the actual area itself is going to be that absolute value of that. I'm taking the positive value. So let's look at that. We'll start with A1 here. So A1 is the integral of my function x cubed minus 2x squared minus x plus 2 between 0 and 1. Okay, so zooming into my function here, we can hopefully see, or not even 0, it's minus 1, excuse me, but from minus 1 to 1 is the region where the function is above the axis. 1, which is the root, is where the function goes below the axis. So the roots are always going to be key points for us in solving these integral functions, particularly functions like cubics where there is that potential for it to go above and below the axis. So you just have to be careful. If you have 3 roots, that suggests, okay, yeah, my function has gone up and down in terms of my axis there, so I just need to ensure that I'm clear on where my function is at all of those points. A lot of the time we will be given a diagram, so that will often help us. If not, we need to make a little sketch of what's happening. Okay, we need to have that little idea for ourselves of what is happening here. So reminder maybe for ourselves that these are roots. There is another root at x equals 1 as well. Okay, so let me just change this here. It should be a minus 1. So let's do my integral. So x to the power of 4 over 4 minus x 2x cubed over 3 minus x squared over 2 plus 2x to be evaluated at minus 1 and 1. So let's fill that in. So 1 to the power of 4 over 4 minus 2 times 1 cubed over 3 minus 1 squared over 2 plus 2 times 1. And then filling in my minus 1 here as well. And that one, just be careful with your negative number when you're filling it into your calculator. Just ensure you are using brackets. Okay, incredibly important to be using brackets here. So let's fill these in. So 1 to the power of 4 over 4 minus 2 times 1 cubed over 3 minus 1 squared. And like you might be able to do half, like we can do half of this really without even filling it in because it's a lot of 1. It's a lot of just 1. So I'm getting 13 over 12 here. Filling in my minus 1 here, I'm just going to go back through my calculation and make all the ones negative. Just makes it a bit easier. That gives me minus 19 over 2. Okay. And that's going to give me an overall answer of 32 over 12. Okay, sorry, that was 19 over 12 there. So 32 over 12, which is 8 over 3. Okay, and that's my area 1. Okay, positive as expected, all is well. Okay, A2 then, the second area, this is the one below the axis. That's between minus 1, or not minus 1, excuse me, that's between 1 and 2. Now, we already know what the integral is going to evaluate to, because it's the same function that we're evaluating. So it's only the bounds that have changed. Okay, I'm missing my dx here as well. So we've already, I suppose, done the integral. So we'll just copy that. I suppose in an actual situation here, we probably would do it out again to ensure that we've definitely got it right. We can also see that there is some overlap here. Okay, and what I'm doing. So we've already done the evaluation for 1 as well. So sometimes if you want to speed yourself up, you can kind of clock onto that a little bit and use those answers. At the same time, if you want to be 100% sure, doing them out again is kind of a surefire way of having a little check to make sure that everything is working out correctly. Okay, you don't want to kind of make a mistake and then just copy that mistake again when you easily could have taken the minute to just do it out again. Okay, so filling in my value for 2 here now. Two over 3 and minus my value for 1, which was 13 over 12. Yeah, I'm just going to take it. So 2 over 3 minus 13 over 12 gives me an answer of minus 5 over 12. Okay, and a negative answer, which is what we expected, that's an indication that the region I've calculated there is below the axis. So in order to find the total area, we just need to ensure that we do 8 over 3 plus the absolute value of minus 5 over 12. So 8 over 3 plus 5 over 12, which is going to give me, let's see, 37 over 12 as my total area, units squared. Okay, so just very, very important there to have that idea in your head already, that you don't just kind of run through it, throw that answer in, and end up with a lesser answer than you should be. So you can kind of see what we mean when we say that if you don't make that adjustment of splitting up the regions, then you run the risk of area 2 there actually nearly being subtracted from area 1, which would nearly mean that we'd cut off a region of this size from area 1 and end up only working out what was left there, when in actual fact, of course, we need to add it on. Okay, and it's just having that idea as you go into the question, just making sure that you're kind of going into it with that thought already. So let's look at the second part. The curve y equals 12x cubed minus 48x squared plus 36x crosses the x-axis at 0, 1 and 3 as shown. Okay, so those are roots. And what's important about that, I suppose, is they're telling us straight away there are 3 roots. For a cubic function, that means it has a part above and a part below. Okay, without a doubt, there's obviously a region above and below. Even if we'd no diagram here, that would be kind of clear just from the description that's given to us. Okay, I suppose important for us just to make sure that we're happy with, you know, which part is above and which part's below. Because it's a positive cubic, I'm kind of expecting it starts going upwards, then down, and then goes upwards again, because a positive cubic will always kind of have that sort of shape. Okay, the diagram given to me helps me out. It's a fairly simple diagram. We could have done kind of a sketch of that as well. We're going to split out the areas. So area 1 here, area 2 here, and make sure that we know the total area is going to be A1 plus the absolute value of A2. We're expecting a negative value for A2 there. Okay, what I'm going to try this time is I'm just going to do or compute the integral for the function here, and then we will evaluate it at the different regions that we need to. Okay, so let me see, the overall integral is going to be so 12x4 over 4 minus 48x cubed over 3 plus 36x squared over 2. And let's work that out a little bit better. So that's going to be 3x to the power of 4 minus 48 divided by 3 does work, 16, and 18x squared. Okay, so let's look at our individual areas now. Area 1. I'm going to want to evaluate this integral from 0 to 1. Okay, so let's look at that. So that's going to give me 3 times 1 minus 16 times 1 plus 18 times 1 minus 0. Okay, if we want to just make kind of straight away that assumption there, really that's just going to end up as 0 for myself. Okay, so yeah, so 0 there. Let's fill in these other values. So that's 3 times 1 minus 16 plus 18, and that's going to be 5. So 5 minus 0 gives me an answer of 5 for area 1 here. Okay, for area 2, and again we're expecting this to be a negative answer, we are integrating or evaluating the same function from 1 to 3. Yeah, 1 to 3. So 3 times 3 to the power of 4 minus 16 times 3 to the power of 3 plus 18 times 3 squared minus 3 times 1 minus 16 times 1 plus 18 times 1. Okay, so let's work these out. So we'll start with the 3 first of all. So 3 times 3 to the power of 4 minus 16 times 3 cubed plus 18 times 3 squared minus 27 minus, and then the 1 then we already know is 5 So that's going to give me minus 32, okay? A larger quantity, expected, a negative quantity, expected, okay? So we just have to be careful when we come to find the total area. Okay, so we just make sure that we take the absolute value of that, get 32. So the total area is 5 plus 32, which is 37 units squared. So that idea of just us making that recognition that area 2 needs to be positive, the 32, and then adding those together. Okay, it's those kind of small little things that are going to kind of help us out here. But really, the main thing here is, I suppose, that extra little understanding that area can, or the calculations I do in terms of my integrals, could be positive or negative depending on where I am on the axis. If I'm above the axis, it's positive. If I'm below the axis, it's negative. I suppose when I was talking about the area under the curve, obviously if I'm below the axis, that area technically is above the curve, but it's the same idea. It's the area from the curve to the axis, and it gives you a negative result. And then if I have a curve that goes both above and below, I'm just going to separate those areas to ensure that I don't kind of cross over my calculations or kind of result in any kind of miscalculations there on account of the difference in signs. Okay, so just making those kind of changes, that's kind of the key things then for those questions where the areas maybe go above and below. And we'll see that a little bit now in the next little parts. So last little part with area then is between two curves. So that'll be your next little one. And then we've kind of our 4 series for area done.